So we have localized states. So we have, for example, system periodic arrangement of atoms. We consider this point one-dimensional case. And we have localized states. We consider only one localized state to the given atom. The energy of such state, for example, alpha or minus alpha, it depends on the notations. And then the question is, how can we describe the coupling between the different states? So we need to introduce some parameter, which is called Hopin integral, parameter gamma, which is sometimes it's defined with a negative sign, but again, it doesn't matter. It depends on the unit, it can be positive, negative. It's a matrix element. So if you introduce wave functions localized at two different atoms, so it's, for example, of course, each wave function has the same profile. So we can call this a profile, which is a C0, and they're localized at different atoms. Then this parameter gamma is a matrix element between the wave function C0 localized at atom X, for example, at 0, localized at 0, with the Hamiltonian of the system, and the wave function localized at the next atom. So A is the period of the system. So it's a nearest neighbor coupling. We consider only the coupling between these two states, nearest neighbor states. And to characterize this coupling, we need to introduce the matrix element between the wave functions localized at nearest neighbor states. So this is a characteristic of this time-binding model. There are two parameters. The first one is the energy of a single of this level. So the energies will be exactly the same for all levels. And another parameter is the coupling between the nearest neighbor states. Such coupling can be it's a Hopin integral. It describes effectively the hopping of electron between two nearest neighbor atoms, nearest neighbor wells. Now, how can you find the corresponding energy, dispersion, and something like that? So it is convenient to introduce, to describe the system with the time-binding model. So if you introduce the creation and annihilation operators for electron at a given site, so A plus M and AM, so they create and annihilate electron at a site M, so it's a site 1, 2, 3, and so on at site M. Then the Hamiltonian of the system within this time-binding model, so-called time-binding Hamiltonian. Again, it's more easy to write down this Hamiltonian, the second quantization approach. So first will be negative alpha, sum over AM plus AM. So it's an electron localized at a given site M, and this is the energy of the site. So it's a diagonal term. Plus we need to add, or in this case it will be with minus gamma, coupled with the nearest neighbor site. So it means it will be of this form. So it will be A plus M, AM plus 1. Plus N, and this it's the nearest N plus A, so it's a complex conjugated M plus N, A, M. So N in this case is 1, so it will be plus minus 1. So in other words, the meaning of this Hamiltonian is that, so we have the localized state at atom M, so it will be coupled to the state at atom M plus 1. And this coupling is described by this, so it means it will be hopping of electron from one state to another. So it means that we annihilate electron state M plus 1, and then we create electron state M. So it describes the hopping of electron from one state to another. And of course, it will be a complex conjugate, so you need to add the Hermitian conjugated part to this Hamiltonian. So this is the meaning of this type of coupling between the nearest neighbor sites, nearest neighbor states, and this is described in terms of this Hopin integral. So we can introduce in terms of the second quantization approach. So this describes, so we annihilate electron in this state M plus 1, and then we create electron state M. And this corresponds to we annihilate electron state M, and then we create electron state M plus 1. So again, it's hopping between these two nearest neighbor states. Then if you use the second quantization approach, we can write down the corresponding eigenvalue equation. So the energy will be E AM So it will be minus alpha am, for example, plus, minus gamma. So we need to consider the commutator of Hamiltonian with the state m. So it will be minus gamma sum, or in this case it will be not the sum, it will be just a m plus 1 plus a m minus 1. The reason is that because we consider, so this is how the state at atom m will be coupled. So we have state at atom m to be coupled to two states, at atom m plus 1 and m minus 1. So this describes the coupling between these two nearest neighbor states. So we write down the energy at eigenvalue equation at state m. So in this state will be coupled to two nearest neighbor states, m plus 1, m minus 1. Then solution of this equation. We are looking for the solution of this equation in the following form: am plus or minus, it doesn't matter. So it will be exponent I k x m a some profile. So this is not solution of this equation, it will be some function. So the amplitude of the state m, so it will be determined by this matrix. So let's call this in terms, not in terms of a. So it's called in terms of the amplitude of electrons at state m. So it will be exponent I k x m and some kind of constant. So another way we have the amplitude of these electrons at different states determined by this type of vector. So we're looking at this solution in terms of some parameter k. So in terms of the real wave functions, not in terms of the quantization approach, but real wave function, it means that the solution has the following structure. C is a function of x, it will be exponent I k x m c x minus x m. And xm is an atom localized at a given point, so xm will be a times m. So another way we can write down a times m, a times m. So it means that the wave function has the following profile solution. So this will be psi0, wave function localized at a given, psi0. So this is a localized at a given at a different atoms. So it describes x, this wave function localized at atom m, to be localized m. A is the period of the structure, the distance between the nearest neighbor atoms. And we introduce this phase vector. So it means that each wave function needs to multiply by this phase vector, so it will produce the, this is effectively how we couple these states. Now if you substitute the Hamiltonian equation, then we produce the following solution. So it will be E will be equal to negative alpha. So the amplitude will be the same at the same states, minus gamma. Then this amplitude are different states, so we need to change m plus 1 and m minus 1. So in this factor, it means that effectively we change m plus 1, m minus 1. So, okay, let's write down this more correct equation. So it will be E exponent, so we consider the amplitude as a given state m, I, k, a, m. Then the wave function, negative alpha, exponent I, k, a, m, minus gamma. And then we write down the amplitude to different states m plus 1, m minus 1. So it will determine proportional to this vector. M minus 1, m plus 1. It will be exponent I, k, a, m plus 1 and minus 1. M plus 1 plus exponent I, k, a, m minus 1. So this is a eigenvalue equation. K is a parameter in this case, and you can see we have I, k, m, a, I, k, m, m, I, k, a, m the same, so we can cancel this I, k, m, and from this equation finally we derive the energy spectrum. So it will be negative alpha minus gamma, exponent I, k, a, plus exponent negative I, k, a. So now you can see that this energy depends on parameter k, so we can add this to exponent, so we produce twice of cosine ka, And this will give you the energy spectrum of the time binding model. Minus twice of gamma cosine Ka. So energy dispersion of the time binding model, and the idea of this energy dispersion is that how we can construct. So we introduce the coupling between the nearest neighbor states. So we have state at atom M to be coupled to this nearest neighbor states. And this coupling is described in terms of these exponential factors when you write down the energy spectrum. So we can generalize this expression to coupling with the next nearest neighbor states. So let's look at this expression. So again, the idea how to find the energy spectrum. So we have state M, so it will be coupled to state M plus 1, state M minus 1. Then the energy dispersion will be minus alpha. So it's the energy of all these levels will be the same, minus gamma, the Hopin integral between the nearest neighbor states, coupling between the nearest neighbor states, to the fixed point I, K, Ka, plus exponent minus I, Ka. So it describes the coupling to state M plus 1, M minus 1. So you need to consider only the nearest neighbor state, how we go from plus and minus K. Now let's assume that we have another coupling with the next nearest neighbor state. This is state M plus 2. And this state M minus 2. It is described as a Hopin integral gamma 1. Then we need to add some extra term minus gamma 1. And this coupling is described by the same expression, but we go into step 2a. So not a by 2a. So it will be exponent I k 2a plus exponent negative I k 2a. And so on and so on. So we can consider next nearest neighbor coupling, next nearest neighbor coupling, introduce some extra term. So in this case, it will produce the following energy dispersion. So it will be negative gamma minus twice negative alpha minus twice gamma cosine Ka minus twice gamma 1 cosine 2 Ka. So and so on and so on. So we can consider generalize this expression for different type of couplings. This is the main idea how to write down the time binding Hamiltonian. So we consider only the nearest neighbor coupling. And then the wave function will be characterized by parameter k, which describes how the phase of the wave function changes when we go from one state to another state. And finally, it produces the corresponding energy dispersion. So if you look only at the nearest neighbor coupling, we have the cosine Ka. And let's look at the corresponding energy dispersion. So it goes like that. So let's assume that alpha is 0. So again, it doesn't matter what is parameter alpha. So energy is a function of k. So it's cosine function. So if gamma is positive, then it will be minus cosine. So it means that it will go like that. And you can see this is a periodic function with respect to k. So it means that we just need to consider one period of this function, because then it will repeat itself. So it's a first Brillouin zone, pi over a and minus pi over a. Then outside of this Brillouin zone, of course, it will repeat itself, so it again will be the same. So it will produce one band. Time binding model will produce only one band, because you consider only one state for each atom. If you consider, for example, one state, then consider another state, and so on, then each state produces the corresponding band, only one corresponding band in this energy dispersion. So, for example, we have the state S type of state. So, introduce the coupling between the same S states in different atoms to produce one band. It goes like that, for example. Then we consider, for example, coupling between P states in different atoms to produce another band. Goes like that, and so on and so on. And we assume that the coupling between S and P states, for example, we have some another state here. This coupling, this type of coupling is very weak. Again, it's approximation, but it means that this will be some kind of independent band, so we don't have any coupling between them. And usually this is a good approximation only when because from this expression you can see that the width of this band is of the order of gamma, coupling between the nearest neighbor sides. So, and this is a good approximation if, for example, the width of the band is relatively small. So it means that we have more or less profile of this structure, so we have almost degenerate levels, and we introduce very weak coupling, so it will produce the following band like that. Then we have another band which goes again almost degenerate, so it will produce very weak coupling, so it means we have very large distance between the bands and so on. So if you need to describe in more correct way, we need to introduce some coupling between the different states, so it will be more correct description of this system. But at least this time-bounded model can capture different properties of the system. At least it's a good approximation to study different effects on solid. For example, if you introduce apply some electric field, so you can study the effect of such electric field on this within the time-bounded model. Now let's generalize this expression. It's a one-dimensional case. Generalize the expression for high order system, for example, for two-dimensional solid, two-dimensional crystal. So in this case we have, for example, let's assume the following arrangement of atoms. So rectangular lattice like that. So the idea how to write down the corresponding energy dispersion. So we start from some atom. So now we have two indices for this atom, for example M and N. And then we go to the nearest neighbor sides, to the nearest neighbor atom. So for example in the x direction, this coupling is determined by parameter gamma x. Then in y direction, the coupling in terms of parameter gamma y. Of course they can be the same, they can be different. And we can say only nearest neighbor coupling. Of course we can look at the next nearest neighbor coupling, but at this point we can say only nearest neighbor coupling. Then the corresponding energy will be minus alpha. So it's the energy of a state. It will be the same for all atoms. Then it will be minus gamma x. So coupling between the state and the same gamma. So in this case, when you go from one state to another state, we just need to change x coordinate of this. So it means that it will be I, k, x will go into, for example, the latest constant in x direction will be a, in y direction is b, kxa plus x point negative I, kxa. Minus gamma y, x point I, ky b plus x point negative I, ky b. So the same idea, we just need to generalize this expression into all possible nearest neighbor coupling. In general, this expression has the following structure. So it will be energy. So this is a simple case of rectangular lattice. So we introduce the coupling in x direction and y direction. This we can find the corresponding energy dispersion. How the energy now depends on kx, ky. In general, we can write down the following expression. So we have the state, which is again atom of the lattice, and then we have some nearest neighbor coupling. For example, it's characterized by these vectors. So it will be nearest neighbor coupling, which is characterized by vector r1, r2, for example r3. It can be many, for example, in three-dimensional, it will be many vectors. Then the energy will have the following profile: minus alpha, minus gamma. For example, we have the same time-bounded model for all directions. Time-bounded coupling. Hoping integral will be the same for all directions. Then it will be the sum of exponent I, k as a vector multiplied by r, I, over nearest neighbor sides. So it will be r1, 2, and 3. And this will be the expression for the energy. So in this case, for example, we have four vectors: 1, 2, 3, and 4. We have four terms, and this is a dot product of vector k and the corresponding vector connecting this atom and the nearest neighbor atom. And the general expression will be the following. So it will be Hopin integral, and this will be the sum over I, and it will produce the energy dispersion. Of course, it will be real number. So for all the system it will be real values, so it will be sum of exponent, but still it will produce some kind of cosine, sine, or some real numbers for the energy dispersion, because the energy should be real. So this is how we can find the energy dispersion with the time-bounded model. So again, we can consider only one, in this case, we consider only one level for each atom, and then we introduce the coupling between the nearest neighbor atoms, nearest neighbor levels. This coupling is characterized by the Hoping integral, and the corresponding energy dispersion is given by this expression. So the advantage of this approach is that it can reproduce some correct properties of this periodic system. So it means that if you look at the energy dispersion as a function of k, it will be periodic. So it means that we need to define this energy dispersion only within the first Brillouin zone. So it means that k should be only within the first Brillouin zone, because outside of the first Brillouin zone, it will be just periodic repetition of what happens in the first Brillouin zone. The same as what we have for the one-dimensional case, so the cosine function of k times a. So we need to consider only the first Brillouin zone from minus pi over 8 to pi over 8. Outside of the first Brillouin zone, it will be just periodic repetition. So it is this advantage of a time-bounded model. So it will correctly produce energy dispersion, and we need to consider only the first Brillouin zone to have the complete picture of this system. For example, when you have two-dimensional case like that, if for example we have A and B are the same and gamma x, gamma y are the same, then the energy dispersion will be the following: E minus alpha minus gamma. So the first term gives us cosine kxa twice cosine kxa and plus cosine kya. For example, the same A and B are the same, sum of two cosine functions. And in this case, the first Brillouin zone will be square. So this will be kx, ky. So we need to consider only this energy dispersion only within the square. Outside of the square, it will just periodic repetition. Pi over a minus pi over a minus pi over a pi over a. And of course, in this case, two-dimensional profile for the energy dispersion. We can draw this profile in terms of equi-energy lines which has the same energy, and this line has the following structure. So we can look. So this will be almost circle, because when kx, ky are almost very small, so we can use the Taylor expansion for this cosine function, and then we can get the following dispersion. So it will be close to the parabolic dispersion. So when it will be minus alpha minus 2 gamma. When kx and ky are small, close to 0, so we can use the Taylor expansion. So it will be 1 minus kx squared a squared divided by 2 plus 1 minus ky squared a squared divided by 2. So finally we have the following minus, so it will be plus 2, so it will be minus 4 gamma, so it doesn't matter, just a constant. And this is how it depends on k. Minus minus gives us 2, so it will be 2 will cancel, so it will be gamma a squared. So this will be kx squared plus ky squared. So equi-energy line, it will be just circle and have the parabolic dispersion. And we can also introduce the effective mass which describes this type of dispersion. So we can write down this term as a k squared h squared divided by 2m star, effective mass. So this effective mass depends on parameter gamma, so we can describe this as a parabolic energy dispersion with some kind of effective mass. Then we go away from this, so it will change the shape. So finally at this point it will be just straight line goes like that. And then so equal energy lines at which you have the same energy. Then when you increase the energy more, then you have the following profile. So it will be the same energy. And if you repeat the structure periodically, then it means that in this, if you continue this periodically, so this is the profile. So again, it will be circle, but close to the edge of this Brillouin zone. So if you continue periodically, again, it will be circle So again, it will be similar to this one, but in this region, the effective mass will be negative. So if you look at the similar profile in one-dimensional case, so it will be cosine function, goes like that. So at this bottom we have the positive dispersion, so positive effective mass, so it goes like that, positive effective mass, and this region, again, if you continue this periodically, it goes like that. So again, we have parabolic dispersion relation, but with the effective negative effective mass at this point. Similar to this case, in this region we have positive effective mass, in this region we have negative effective mass, so it has profile which goes like that in two-dimensional case. So this is the illustration of the time-binding model. So it's an example of a strong periodic potential, and we consider the hopping between these strongly localized states as a perturbation, which introduces some kind of effective kinetic energy, the effective motion of electrons through this system. And this kinetic energy is described in terms of effective momentum. So we can consider this K as some kind of effective momentum. Of course, it's not the real momentum, but it's the effective momentum of the system. Describes the propagation of electrons through this system. And the advantage of this time-binding model is that it can produce the correct dependence of the energy on the parameters K, X, parameters of the wave vector. So it has correct periodicity. So we just need to consider energy dispersion within the first Brillouin zone, and then it repeats itself periodically. So it's correct property of the system. So, but this again, this is the approximation which is valid for the case of the. But there are a lot of applications time-binding model because it can describe, at least capture main properties and crystal. It captures also the crystal symmetry of the system. So it means that it can correctly reproduce, so we don't need to worry about the how to construct the first Brillouin zone. It will produce automatically the correct Brillouin zone in terms of the dependence on wave vector. We just need to provide the orientation of the nearest neighbor vectors. So we need to tell if this is a site, we choose any atom, and then we connect this atom to the nearest neighbor atoms, and then you can construct the corresponding, find the corresponding energy dispersion, and it will have capture correctly the band structure and correctly the periodicity of the system and so on.